Welcome to today's webinar. The topic today is integration of RFEM 6 with web applications using Webservice Python library. My name is Andreas Herold. I'm responsible for marketing and public relations in the company Dlubal Software. For instance, the Dlubal website, the German and English webinars, customer projects, and so on. I will be the presenter today, and my colleagues who also participate in the webinar can introduce themselves.
Hi, my name is Doğukan Karataş and I'm the product engineer at Dlubal Software. I am responsible for developing and testing web services and API tools, and I will be the presenter of today's webinar.
Hello, my name is Jaroslav Broš, and I'm the leader of the team which is responsible for the development of web service scripting and the interfaces. Today, I'm here to reply your questions which you will have during the webinar.
Hello, my name is Frank Faustich. I'm responsible for quality management and product engineering. I'm also working on the Python interface in our program, and today I will answer your question.
Okay, thank you for your introduction. Then we can switch off our webcams that the attendees can see the full screen. Some words how you can ask questions. You can show or hide the panel with that arrow here, and then you can enter a short question here, and my colleagues will answer you. If you don't get an answer during the webinar because there are too many, you will get an email afterwards. The other way is to watch the entire webinar and then email questions to info@dlubal.com. Then we will start. I hand over the screen to Doğukan. Doğukan, it's your turn.
Okay, so I hope everyone sees my monitor now.
Yes.
Okay, great. So, okay, I'd like to start with a presentation about web service and API technology and explain it to you briefly. As you know, the goal of this technology is to provide an easy-to-use programmable interface for RFEM 6 and HTOP 9. With this, you can easily program and interact with our software. For those who may not be familiar with programming, do not worry. I will guide you through every detail step by step, making it easy for you to understand and operate. As a team, we at Dlubal are continuously developing comprehensive frameworks to simplify the programming experience. Our framework has been developed in Python and C#, and also scripting in JavaScript is also available. This framework provides you with a wide range of tools and options to make your programming experience easier. So today's topics include a true explanation of the main logic behind the technology, including the key ideas behind APIs and web services, as well as how they work in practice. And then a comprehensive overview of recent developments in web services, along with a detailed roadmap of our future plans for the technology. And the third point is step-by-step instructions for installing our Python library and getting started with using our web services. And lastly, I will show you two live coding examples to help you better understand how to use our technology in practice. The first example will focus on optimizing a still storage tank, while the second example will demonstrate how to create an easy web application using RFEM web services. Okay, so what is an API? API stands for Application Programming Interface, which is a set of rules and protocols that software programs can follow to communicate with each other. It essentially acts as a messenger, facilitating the exchange of information between different programs or services. By receiving requests and translating them and returning responses, it enables the smooth transfer of data and functionality between different systems. To illustrate this concept, consider a graphical user interface which serves as a communication protocol between humans and software programs. With the GUI, you can interact with the program using buttons, menus, or other input methods. In the same way, an API allows software programs to interact with each other by providing a standard set of rules and protocols, for example, JSON and XML in this case for the communication. For example, let's say you're using the RFEM interface to give the program some comments using buttons or inputs. With an API, you could similarly enable communication between one software program and another. This could include sending data from one program to another or using one program's functionality within another program. By providing a common language for different programs to communicate with each other, APIs make it easier for developers to build complex systems and integrate different technologies. So actually, web services are a type of application programming interface, but that distinguish itself from other types of APIs based on their style and way of communication. Web services facilitate XML-based information exchange between systems. In our case, we use a HTTP technology called SOAP, stands for Simple Object Access Protocol, to establish this connection, which provides a standard method for accessing web services. Our team has developed frameworks that enable the use of this connection in structural analysis and design. These frameworks provide basic functions that allow users to send commands to RFEM and receive responses. They are designed to be user-friendly, so even users with minimal experience can use them effectively. So what is the difference between COM and web services and why we change our method? So RFEM 5 is a Windows application that can only be run on Windows operating system. This means that users who do not have a Windows operating system cannot use the RFEM 5 software. However, with the introduction of RFEM 6, users can now use RFEM 6 regardless of their operating system. Another reason for the change is that COM technology, which only runs on Windows, has native support for C and C++ programming languages. These programming languages are currently used by a relatively small community. By using web services, our product can now be used by a majority of the programming community. Moreover, Python, C#, and JavaScript are easy to learn, and there are many resources available online for beginners. Making the shift from COM technology to web services is a significant change for our product, but with web services, we can now reach a wider audience and provide easier access to our software. Okay, I would like to highlight the new features we have implemented since our last webinar and emphasize 3 important points that mostly requested by our users. The first and most important point, in my opinion, is the direct access to the result tables. With this feature, you can access any type of result after your calculation and filter these tables to show minimum or maximum values. We are still working on accessing the design check tables for the results, but which I will mention in our roadmap. The second point is the ability to access and export printout reports. With this functionality, you can access your printout reports and export them as HTML or PDF. This is a great feature for optimizing your reports. The third topic is the development of input configurations for our design add-ons. This is an ongoing process, but our priority is in steel, concrete, and timber design, and this enables our users to define configurations for our design add-ons. Okay, so I believe that transparency between us and our users is essential for the success of our development plan. Therefore, I would like to outline our short and long-term plans for web services. In the short term, we have 3 priorities. Our first priority is to extend design add-ons in our result tables. We are in the final phase of this development, and this feature will be available to our users soon. Secondly, we are working on the ability to get and set mesh points for finite element analysis. This is crucial for defining and reading results for every mesh point. And lastly, we plan to implement simple web applications that have the same functionality as our desktop blocks. This will allow our users to implement their web applications with web services. By implementing these short-term goals, we are setting the foundation for our long-term plans. We will continue to work towards improving the functionality and accessibility of our platform and remain committed to transparency and open communication with our users every step of the way. To get a detailed insight of our development plan, you can visit our GitHub page. Under the projects table, you can track all the to-dos we have planned for our development under long-term or short-term Kanbans. If you have any requests for our tool, please reach us and we will reconsider our priorities. So there are 3 ways to access our Python repository. First is, if you don't have a GitHub account, you can download the repository statically as a zip file. The second is, if you have a GitHub account and using Git Bash, you can clone the repository in your local using Bash terminal. The last and the best way, in my opinion, is installing the library in your machine via pip install. The advantage is you can refresh it with the new developments easily. If you have Python installed in your computer, all you need to do is just open the command prompt and type pip install RFEM. When it's done, you can access the RFEM Python library in every part you want in your device. Let me quickly show you the repository and how to install the libraries. So if you go to github.com, Dlubal software, you can see our repositories here, and you can go to the RFEM Python client. Now here is the option to download as a static zip file, or if you want, you can go and check how to download our page, and there is some RFEM package, as you can see here. Now this is the command for installing our library via PyPy. Then you can see our source code, examples, and of course our developer documentation. So if you go to our developer documentation, you can see we have some guide here for RFEM Python client, RStub, R section, JavaScript commands, some articles, and some tutorials. For example, if you go to the articles, there are some useful tips how to use our Python library. If you open the, for example, still design, you can see how to define still design serviceability configurations, what is the functions and the parameters. You can quickly check our Dlubal developer documentations, and it will be helpful for you. Okay, so I think now I can jump into the examples quickly. So I'll use Visual Studio Code. Let me open a folder here. Yeah. So the first example will be a simple tank, still storage tank, but after that I will optimize the wall thickness of this simple application. Okay, so first I need to create a Python file. Let's say this is tank-app.py. Okay, so first thing I need to do is import our Python RFEM Python libraries. So the first library will be our init model class, because inside I can find model and calculate all classes, which is crucial for initialization of the program. Then I need some basic objects. For example, I can go import material. Then from basic objects, I can import node. If you want, I can quickly show you how this import is working really, because this RFEM is, as you can see, is the folder. The basic objects is the subfolder. The node is the name of the file. And then finally, this node is the name of the class. So I'm importing this class here. Okay. So then I need a line. And because I'm going to create some thicknesses, I need the thickness. And finally, some surfaces for my tank. Okay, I think that's enough for creating a geometry. If I need another imports, I will go back and do my imports also. So I want to add some parameters to make this example a little bit parametric. So let me add something called diameter. Let's say this is 8 meters. Height, let's say this is 12 meters. And I'll add something called util, stands for utilization. So I can control the percentage of the water inside the tank. So let's say this is 80%, so 0.8. And then something for wall thickness. Let's say begin with 7 millimeters. I'm typing it because of the meter. Okay. After creating this, now I can call my model class. When I open my brackets, I can see the attributes. Because my RFEM has no model at the moment, as you can see, I'd like to pass the first attribute as true because I want to create a new model, and I will name it as tank app RF6. Then I'll go to my service class and I want to delete everything all. I know there is nothing open actually, but sometimes RFEM can inherit some properties from the previous models. Therefore, I'm always adding this delete all if I want to begin from the scratch. Then I'm telling RFEM that I'm beginning my modification. After that, I'm telling RFEM I'm finishing my modification. Then I can put everything, every code I want between these two lines. So let's begin with creating a material. I will create a material for steel. First attribute is the number of the material, so this is material 1. The second one is the name of the material, which is a steel material is 235. And then I want to create my nodes. The first node, so when I create the node class, what I have to pass is the number of the node, x, y, z coordinates. So the first node will be in the diameter divided by 2, 0, 0. This is the bottom node. Then node 2 is same with the x, 0, but at minus height. This is the top node. Why this is minus? Because I'm using my RFEM z downwards. That's why I typed minus here. Then I created my two nodes. That means I can create my circles because I want to create a quadrangle surface. I need 2 circles and 1 line. So when I call my class line, and if I use dot notation, I can access the static method circle. I can quickly show it to you. As you can see, this is the class line. And inside the class line, we created some static methods, which is easily creating circles, arcs, or other type of lines, for example, elliptical arc and so on. So that's why I'm using circle method here. So this is the line 1, and the center of the circle is 0, 0, 0. Circular radius is diameter divided by 2, and the normal point is on z direction, so it should be 0, 0, 1. Yes. For the second circle, I'll just copy and paste and change the number of the circle and also the z coordinate of the circle. Yes. Now I have 2 circles and I need a straight line between this circle. So this is line 3 and this is between the line number 1 and the 2. Sorry, not number 1 and 2. Yes. Now that should create my circles. Let's quickly check. I'll divide my screen easily. And let's run this. Every time you see the connecting to server, that means this script is running. Then it's creating a new model called tank app RF6. It has created the material for the steel, the nodes I want, and the circles. For example, if I just change it to 4 and run it again, now the height will be 4 meters. Yes, it's running. Let's just stick to the 12 now. And then it's time to create my surface. Okay, so for this, first I need to create a thickness. This is the thickness 1. Let's say the thickness name is wall. Okay, I'm going to use the material 1, and uniform thickness will be the wall thickness. Yes, because I already defined it here. Okay, then I can create my surface, and I will use dot notation again and use the standard surface. Okay, this is surface 1. As you can see, there are some enumeration items here. This is some classes we created for you to use some selections easily. So if you go RFEM enums, and you can import this classes easily, for example, surface geometry. This allows you to select some geometries you can see here. Okay, so in this case, I'm going to create a geometry quadrangle. So I've selected this, and then geometry type parameters, it's between the node number 1, 2, and this is empty. I just need this node. And then boundary lines is 1, 2, 3, and finally thickness is 1. Yeah, so after that, maybe I can add a line support. Let me just quickly import it also from the types for lines. Line support, import line support, yes. And I need to import my line support type from the enums too. So I'll create my line support here. Line support 1. I need it on the line 1, and line support type is, let's say, hinged. Okay, quick check again. I'm expecting to create my surface and the line support. Yes, my surface is created and also the line support. Okay, great. So next thing we need to do is, for the calculation, we need to create some loads. So this is a still storage tank. Let's imagine this is containing some water. That's why I need to create some pressure inside it. So first of all, I need to create some analysis settings. So I will import static analysis settings. Yes, and also load case. Okay. Now I'll create my static analysis settings. I'm just going to, I'm not going to type any parameters inside because I'm going to create a linear one, so I don't have to type anything. I'll just use the default parameters. Then I'll create my load case. This is the load case 1. Name of the load case, let's say this is the pressure. And then for the self weight, I'm just calling false. I don't want to use the self weight of this load. Sorry. Okay, so it's time to create my surface load. So, but I didn't import it yet, so I'll go here from RFEM loads, surface load, import surface load, yes. So I'll use surface load close method. Okay, so the number of the load is 1, the load case number is 1, and the surface I would like to assign is 1 again. Then I need some enumeration items, load direction and load distribution. Let's quickly import them also. Surface load distribution, surface load direction. So surface, let's check the, yes, so I need the direction first. Surface load direction is, we will select load direction local Z. And for the surface load distribution, we will select varying in Z because it's a pressure. Okay. Then it's time for me to create some load parameter, but maybe I don't know what the load parameter is. I can just quickly scroll down here. And then for the load distribution varying in Z, load parameter is a list of lists. And this is distance, delta distance, and magnitude. Okay, so I'll just create my list of lists here. Yes, yeah. And the first row, I will start with the load height. So minus load height. Oh, I didn't create a load height yet because I need a variable called load height to find where the water is standing actually. So let's call it load height, and I will multiply the utilization between utilization with height. So this will tell me the meter of the water. So for the first attribute, I will begin with the load height because this is the top point and I don't want any pressure here. So I'll tell this is 0. And then for the second, I'll start with 0. Distance is 0. Delta distance is load height. And then the pressure should be G multiplied with load height. And this is multiplied with density. Okay. So this should create my water pressure. Let's check again quickly. If we typed everything right. Okay, the pressure load case has created, and this is the varying in Z pressure load in the tank. As you can see, this is the distance, delta distance, and the magnitude, the list of lists, as you can see here. Okay, this is done also, so I can just go and calculate everything. Then this is the cool part. I can read the results just from the Python. I don't need to go to the RFEM at all. So I will go here from RFEM results, result tables. I will import my result tables from here. Then I'll import my results. So what I want is to read maximum equivalent stress on the tank wall according to the von Mises. So first thing I can do is to import all the tables from the result tables. Surfaces equivalent stress misses. Yes, this one. This one will return me the result table for von Mises stress method. But stress table is a real complex structure. If you want, I can show you quickly how the stress table looks like in the terminal. I can print it. Now a new model is created, mesh has generated, and calculation is started. Now we can read the results. Okay, as you can see, the stress table has a lot of things inside, and it's a little bit hard to find your way inside. So for this, we just created get max value and get min value functions, and you can go quickly and say, okay, my maximum stress is get max value from this table, and for which parameter? So equivalent stress sigma max, right? So I can just maybe quickly copy and paste it, but not minus, I want the max. So yeah. And then I want this value according to the megapascal. So I think I need 6 zeros. Yes, 1, 2, 3, 4, 5, 6. Yes, okay. It should be megapascal now. And then I can print my results. For thickness, wall thickness multiplied with 1000 because of the millimeter, maximum stress on the tank wall is max stress. megapascal. Let's divide my screen again. And then I'll clean my terminal and run it again. Let's see what's the result now. Okay, mesh is created, calculation is started. And yeah, for thickness 7 millimeters, maximum stress on the tank wall is 63 megapascal. Okay, that's cool, but let's add something else. So let's say you want to have a tank wall stress below the 50 megapascal. And you want to find out which wall thickness I need for this. So you can just go quickly here and create a while loop and say while maximum stress is bigger than 50, do this procedure again and again until it's below 50. So for this, at the end of every loop, I'll just add wall thickness 1 millimeter. This plus equals to 0.001. And then finally, I can say print f selected thickness as selected thickness as I'll just round my value because I don't want any floating number like 7.59. I just want 7 or 8, so I'll round it. Wall thickness 2, and I'll multiply it with 1000. And of course, I need -1 because I want the iteration, but the before one. So this is the millimeter. Okay, we will see. So, but of course, I need to tell this program a value for max stress because I defined max stress here, but I'm using it before, so it doesn't know what is the max stress first. So we can just give a big value. It doesn't matter, bigger than we expected. Let's say 200, and then this will begin. So let's switch to the divided view now, and let's start calculation. Maybe clean the terminal. Yeah. So first model is created. And here is the result. For thickness, 7 millimeter, maximum stress on the tank wall is 63, as we did. But since it's bigger than 50, it's going on. For 8, 55. Still bigger, doing it again. For 9, let's make it bigger. It's 48. So selected the thickness is 9 millimeter. I just quickly created a little optimization parameters for your tank walls. We can change these parameters, initial parameters, and do whatever we want if we are working with these steel tanks, for example. This is my first example, and yeah, I think I can quickly jump into the second one. And the second one, I would like to show you a quick web application which we can control RFEM. Okay, let's clean our RFEM first. Close this. Yes. Clean our terminal too. Then let's call it web app.py. Okay, for this web application, I'll use a Python library called Streamlit. This is an very easy Python library that you can create some web applications. The goal is I would like to show you how you can integrate external Python libraries with RFEM, so how it's easy to use with these functionalities. So secondly, I need pandas library too. Okay. The other imports are just the RFEM imports. I don't want to show you again, so I'll just copy paste it. This is the same imports from the RFEM. I just import everything I need. Okay, so if you want, let's quickly create our page first. So let's create our web page. So I'll give it a title with the markdown. I'm using Streamlit markdown function, and let's say RFEM web integration. And then to start it, I'm going to my terminal and say Streamlit run web app.py. Click enter, and this is the localhost. I need, and let's go to the H again. Yeah, this is my web page now. This is the title. Okay, so now what I would like to do is develop a simple continuous beam application for your everyday beam calculations. But for this, I need an input column and also an output column. So I'd like to divide this scene into two. And maybe now I'm using only the middle phase. I can just say I want to use the whole page. So set page configuration, and the layout is white. And then I can say I have two columns, input column and the result column. And this is Streamlit columns, and I can tell the ratio. Let's do it 1 to 3, 1 to 2, or something like this. So with this, I can begin to give some inputs. I'm telling this because inside the input column, I want this thing. So inside the input column, I want a form, an input form. And this input form, let's give the name, this is the input form, should contain some variables. Since this is a continuous beam application, let's say the first thing is the first span length. This is a number input. And give the name, first span length in meters, and give a value, let's say 3. Then the second span length. Same logic, second span length in meters, and the value is 4. And for every form, I need to add a button. Let's say this is the calculate button, and I'll use form submit button, and the name of the button is the calculate. I just saved my file and opening here, and I'm just clicking rerun. And as you can see now, I have an input form. Now I can give my inputs from here. Okay, let's add more then. This is not enough for us now. So maybe we need material. So let's say set Streamlit text input material, and the value is again steel, and the section is a text input also, and the value is P300. And finally, maybe I can add a span load. This is a number input also, say distributed load in kilonewton meters, and the value is 2. Okay, I'll just rerun. Yes, now I have some inputs that I can control my RFEM. So how I can do that is to connect these variables into the RFEM variables. So I'm saying to program, if calculate button is clicked, do this. So first create a model, of course. So create a new model, and the model name is web app beam, maybe, yes. So creative, then I'll again use the service, delete everything for every new run, then use the service to begin modification, and finish modification. Okay, Then let's create our continuous beam. For this, first I need a material. It's material 1, and the name of the material is, of course, which the material variable I have created here. Then I have section 1, and this section variable I have created here, and I will take from the user. Then I need 3 nodes. Node 1 is at 0, 0, 0. Easy. Node 2 is at first span length 0, 0, of course. And node 3 is first span length plus second span length. Sorry, 0, 0. I have my material, I have my section, I have my 3 nodes, so I can create my members. So member 1 is starting from the node 1 and at node 2. I don't need any rotation angle, and start section is 1 and section is 1. Member 2 is beginning at node 2 and at node 3. No rotation, and the section is 1. Okay. So I'm curious now, how does it look like with RFEM? Let's split the screen again with our web application. So when I click calculate, now it's running, as you can see. Now first it will create a new model because there is no model, okay? Then it will create a continuous beam. Okay, delete all has a method not found because I typed it wrong. Yes, too much else. Rerun again. Calculate. Okay, connection has started. And it has created my continuous 2 BIMs, as you can see. But this application is always logged. So there is a method that you can cut this application logged comment every time. So I think it's useful. So I would like to show it to you. Client model service close connection. So every time when I rerun, this connection is going to create it and then closed. For example, let's say I would like to create HA 300. And this will be the new one, or span length. Let's make it bigger and calculate. Now it's bigger, so I can control everything with my inputs here. And there is endless possibilities. You can create some select boxes or sliders and everything, and you can control your RFEM with this web applications. So we connected the geometry, but we still didn't connect the loading. So let's do it. So after the member, I should add some nodal supports also. This continuous beam has no supports yet. So nodal support 1 at node 1, 2, 3. And the nodal support type, I can use it, or I can use a list of some values. Let's say infinite, infinite, infinite for the translation, infinite, 0, infinite for the rotation. What does it mean? So let's check at the RFEM. I'll run this again, and it has created my nodal supports, as you can see. So if you can go here and check, you see for the support conditions, I just said for the X infinite, Y infinite, Z infinite, as you can see. For rotational Y, it's 0, and then the infinite. So I can control everything in my support with this list. Okay, so after the nodal support, I need to create a static analysis settings again. So this is static analysis settings 1, and let's call the name as linear, and then I need a load case. The load case 1, name, I don't know, load, very creative again. Then I can create some member loads. So my member load is, this is the first one, and the load case is 1. Again, I want it on the member 1, and the magnitude is equals to span load, which I created in the GUI, multiplied with 1000. Okay. This is the same for the second member, so I can just quickly do this, and yes, now I have connected the loading to. So let's make it for IP 200 and distributed load 2 is cool. Let's say calculate, and let's check if our loading is also working. Okay, load case is created. Let's see the loads. Yes. So what happens when I change it to 13? Yes. Now I'm controlling this load with this box here. So, okay. After that, what I would like to do is to calculate everything, then read the results. So before closing the connection, I need to calculate everything. So let's go here. Calculate all. And then it's ready. Now it's my turn to read the results. So let's do it. Before that, let me just quickly add a simple table so we can see the default table, then we can put some values inside it. Okay, so for this, I'll create a data frame called results with the columns. Oops, the columns here. Members, maximum displacement in millimeters, and let's write the maximum bending moment here in Newton meters. Then let's give some default values for the members. Let's call them first span and second span. Yeah. And for the maximum displacement, take this bar here. Yes. And let's say it's 0, 0. And then just copy and paste it for the maximum bending moment, 0, 0. Then I can now create a table, right? So I can go here and say with results column, just put this table there. And then rerun. Yeah, now I have a result table here. Maybe a simple title could work here. Result table. Yeah, cool. Okay, so what I need to do is now, after every calculation, reading every result and writing into this table. Okay, so for this, let's start with the displacement. For the first span, I'll read the displacement table. This table first, I'll call it. I'll go to result tables. I'll read the members, global deformations, and read the case object type. Load case, it's coming from a load case, loading number 1, object number 1. Then the first max displacement is to get maximum value from this table. Displacement table first, then read the displacement absolute, then multiply it with 1000. 3 zeros I need, yes, okay. So the second table first is the same. Result tables, maybe I can just quickly copy and paste it. It's just 2, and then just copy and paste this one too. But this is, let's call it second max displacement, and this is the second table first. And displacement absolute, yes. Now I have read all my displacements. Now it's time to read my moments. So let's say moment table first. Where is the moment table? I can find it under members, internal forces. Again, from a load case, loading number 1, object number 1. Then max moment first is equals to result tables. No, sorry. Get, this time I'm going to use get min value because the maximum moment here is a negative value. That's why I'm using get min value function. Then internal force my. Yeah. So let me just quickly copy and paste it for the second one. Just change the names. Let's call it second. Let's call it second also. And this is the object 2, and this should be changed to. Okay. So I have read my results actually for the displacement and for the bending moment for the first and second span. Now I would like to write this new values to my result tables which I created on web. So what I do is simply just update my data frame. So for the displacement, for the displacement, it's first max displacement and the second max displacement. And then for the moment, maximum bending moment, it's maximum moment first. I think I need to divide it by 1000, yes, because I want kilonewton meters, max moment second divided by 1000, and it should read the results and give it to us. Let's try once. So it's running. Let's check the RFEM. Calculation has already started and ended. Now I can see the results, but this doesn't seem to correct to me because this shouldn't be same. Yes, they are the same. Let's check the RFEM itself, so we can go to results. So we can check our results here, and then we can check our bending moments here. So one of them should be get max value, not min value. I think I used get, yes, this one should get max value. So let's rerun this, split the screen, and give another values 5, 3, I don't know, IP 270, and distributed load is 15. Calculate. A new beam is created. Yes, calculation is done. And then, as I can see, this is the result here. This is the result here. And then for the displacement, 6 and 0.4. Now I have my results in this table. Now I can control everything in RFEM in this web application. This is just up to my creativity. For example, I have just created a simple graph to show you today, but it's irrelevant and it's too long. I'm just going to copy and paste it. That's all. I am not going to code it live. Then, for example, I'll create a simple graph just after the inputs. Yes, here. So I'm using Plotly graph objects, so I need to import them. Import Plotly graph objects as go. Yep. I have just added a simple. Now I just add the default figure, but not on the results column. So just add it here. Plotly chart default figure. Okay. I'll rerun this. Now, as you can see, it's a basic graph to visualize something. For example, if you change this, and if you change the loading, I don't know, 6, and if you change this to 12, let's say calculate, and graph will be updated, and also the table will be updated. You see my graph is now 6 kilonewton meter, and here is the section, and here is the results I can see here. Okay, I think this is a good example how you can integrate your web applications inside the RFEM using web services. And I think that's all I would like to explain for today. I hope we will see each other with some good and exciting examples in the next time. And thanks for listening.
Okay, Dlubal, thank you for the nice presentation. Before we close the webinar, I would like to share my screen that you can see where you can find the recording the next days on our website, dlubal.com, under News and Events. You can find the webinars. That's today's webinar. Those are the webinars that we scheduled the next time. Okay, I click on it. And yeah, you will also get a link with this attendee certificate, and yeah, well, will get an email with a link to that page and a link to the attendee certificate. You will find the recording here in the middle of the page. Here are the presentation slides, and we will also upload the model and the files here. Okay, if you want to try out this webinar, for example, then you can download the free trial version here above, free trial version. And the web service is also included in a demo mode. And you can try the version of RFEM 6 and also RSTAP 9 for 90 days. If you have further questions to add-ons to web service, or you want to have that we present presentation for you, only for you, for certain applications also, then you can find under support and learning here, contact our sales team. You can got an offer and so on. So that should be also all from my side. Maybe a last hint: when you leave the webinar, there's a small survey. You can score the webinar. You can enter wishes for future webinars and so on. Yeah, just note that the worst score is 1 and the best score is 5. Okay, that's all from my side. Thank you for your attention. Thanks to Dlubal for the nice presentation. Thanks to Jaroslav and Frank for answering the questions. I wish all a nice rest of the day. Bye-bye.
Have a nice day. Bye-bye.
Have a nice day. Bye.